All right, now welcome to this session. Now in this session, I will be doing acids and bases. But before we can start with acids and bases, I think it's important to start with these guidelines on what we will be actually focusing on to, so that when we go through the context, we don't have to cover a lot of talking and a lot of explanations. Rather, again, so that you can understand how is this topic actually structured. So now having a look at the first bulletin under the acids and base reactions. Now here's the first question that you need to ask yourself and you need to answer to yourself. Remember, acids and base forms a part of paper 2, which is the chemistry part. Now there are different kinds of reactions, right? We have the acid base reactions, we have the redox reactions, reduction oxidation reactions. There are many different types of reactions, but in this case, we will be looking at the acids, we will be looking at the base reactions. But before we can even talk more about the reactions, we need to understand the terminologies behind this concept, which is called the acids and bases. And then again, we need to understand the theories that are behind this concept and how these acids, how these bases actually interact with one another. How do they actually react? That's also very important. Then now we can talk more of the reactions. Then we can talk more of the calculations based on these reactions. Now, when we talk about the first bulletin, we can see here it's all about definitions. We need to know how to define acid and base in terms of alkenes. We need to know how to define acid or base in terms of Arrhenius. Again, we need to know how to define acids and base in terms of Lorentz theory. There are two theories behind this concept, and we need to know how to define acids and base. Now, firstly, the first theory, it talks about the Arrhenius theory, and then the second theory, like I said, it talks about the Lorentz theory. For both acid as well as the base, you need to know how to define them. According to Arrhenius, he said that the acids produce hydrogen ions in a solution. Now, what does that mean? It means that if you take a base, sorry, if according to Arrhenius, if you take an acid, the H plus ions, the hydrogen ions will be produced in a solution, and then he explained the base as the production of hydroxide ions in a solution, which is OH minus ions, right? So that's Arrhenius. And then later on, during the studies of acids and bases, there were two scientists who came along to solidify this definition of acid and a base, right? So we have two guys, Lowry and Browstead. Their theory, it postulates that an acid is a proton donor and a base is a proton acceptor. Now, the reason why we now have these two guys with their theory, it's because what they have realized how Arrhenius is actually explaining these terms. For an example, there are many different types of bases, right? And there are many different types of bases. Now, let's talk about the base. Now, if we look at, I want the most common base that maybe, I don't know. So now, the base that we know, it is NH3, ammonia. Ammonia, it is a base. But my question is, does ammonia produces OH minus ions in the solution? It actually does, obvious, if it reacts with water. Right. If ammonia reacts with water, it will produce hydroxide ions in a solution. But now, does ammonia turn into hydroxide ions when it reacts? No. So that kind of gives an exception on how a base it is actually behaving. Now, that is why these two guys they came later on during the studies of acids and base, and they have realized that a base it is actually a proton acceptor. So that means each and every type of a base, when it reacts, it will always accept a proton, meaning it will always accept H plus ion. It will always accept H plus ion. So it will accept it. So that's how these two guys define the base. And then how they define the acid, it's the opposite of that. They say that an acid is a proton donor, meaning it will donate or it will give away a proton, which is H plus ion, right? So it's important to know these definitions according to these two theories. And then point number two that we need to understand is You should be able to distinguish between a strong acid and a strong base, a weak acid and a weak base, with examples for sure. Like I said, there are many different types of acids, there are many different types of bases. Some are strong, some are weak. So you need to understand even how are strong acids or strong bases or weak acids or weak bases actually react or actually behave during a chemical reaction. Now, we say that the strong acids, they ionizes completely in water to form a high concentration of H3O plus ions, right? So obvious, this is a strong acid and it will ionizes into its ions. So when a strong acid in water ionizes, it will form a very high concentration of H3 plus ions. Now, there are quite numerous examples of strong acid, but for your curriculum, the strong acids that you're going to focus on to, it is hydrochloric acid. Second one, it is sulfuric acid. The third one, it will be our nitric acid. Right? So these are just quite few examples of strong acids, meaning if you take hydrochloric acid and then you add it in water, it will ionizes completely in water, and that water will have high concentration of hydronium ions, meaning it will have high concentration of H3O plus ions in it. Same applies to sulfuric acid as well as the nitric acid. Now, let's talk about the weak acids. We say that the weak acids ionizes partially or incompletely in water to form definitely low concentration of hydronium ions. So examples of weak acids, we are looking at ethanoic acid. We are also looking at oxalic acids. These are examples of weak acids, right? So if you take the ethanoic acid and then you add it in water, what's going to happen? That's a weak acid. It will partially ionize and then it will form low concentration of H3 plus ions in water. Now, let's talk about a strong base. Strong base, we say it dissociates completely in order to form high concentration of OH minus ions, right? So, meaning if you take a strong base, and then here are the examples of strong bases. We are looking at the sodium hydroxide. We are looking at the potassium hydroxide. So if you take sodium hydroxide and you dissociate it in water, you're going to have a very high concentration of hydroxide ions. Or if you take your potassium hydroxide and you dissociate it in water, you're going to have high concentration of OH minus ions. Same applies to the weak bases. They dissociated partially or incompletely in water to form low concentrations of OH minus ions. And what are the examples of weak bases? We are looking at ammonia. Like I said, ammonia, it is an example of a base, but this is a weak base. We have the ammonia, we have calcium carbonate, we also have the potassium carbonate. These are examples of weak acids, weak bases. Oh, by the way, in calcium carbonate and sodium hydrogen carbonate. So yeah, these are all examples of weak bases. So bulletin number 1, we were talking about defining acids and base by two theories. And in bulletin number 2, we were distinguishing between a strong and a weak base, a strong and a weak acid. By the way, we know what does a strong acid, how does a strong acid behaves in water. We know how does a weak acid behaves in water. We know how does a strong base and a weak base behaves in water in terms of dissociation and ionization. The other one completely to form high concentration, the other one partially or incompletely to form the lower concentration. So, right, so that's what we are learning so far. And then number 2, we should be able to distinguish between concentrated and diluted acid. Now, here's what I want you to understand. When you dilute or when you concentrate either your acid or base, the strength of base or the strength of acid will remain undefeated, meaning it will remain the same. If, say, for example, you have your beaker and then you have your water, and then inside of your water, let's say you pour your acid, HCl, right? Recall that HCl, it is a strong acid. You put your HCl in water solution. And then the more you add water, what is happening? You are diluting your HCl. And remember, HCl, it is what type of acid? It is a strong acid. So the more you add water, the more you add water. Will the strength of this acid change? No. HCl as a strong acid will remain as a strong acid. The only thing that will change it is the concentration. So strong acid remains as a strong acid, whether you add more water or you add less water by diluting or concentrating it, it will remain the same. The only thing that changes or the only thing that's going to be affected, it is the concentration. Okay, so that's why here you should be able to distinguish what is a concentrated and dilute acid or a base. Okay, it does not matter whether you add the base or you add the acid, depending on the strength, that doesn't affect it at all. And then that's what I wanted you to understand. So when we have a dilute acid or a dilute base, what does that mean? Okay, let's start with concentrated. When you have a concentrated acid or a concentrated base, what does that mean? That means you have a large amount, you have more number of moles of acid or a base in proportion to volume of water. So meaning you have more of acid than water. But when you have a dilute or when you have a dilute acid or a dilute base, you have a small amount or less number of moles of acid or base in proportion to volume. So that means here you have, okay, here you have more acid than water, but here you have more water than acid or base because it is diluted, right? Right. Recall that the strength remains the same. Only concentration gets to be affected, or the number of moles gets to be affected in a solution. That's bulletin number 3. Now let's go jump to bulletin number 4 here. So here we should be able to know how to write the reaction equations of aqueous solution of acids and base. Example as follows. We are talking about the acid and the base. And in this case, you should be able to know what is reacting and what does it form. You can take your acid and react it with base and form your products. You can take your acid and react it with water, or you can take your base and react it with water. So what I want you to understand is we can have different types of reactions under acids and bases depending on what it is reacting. Okay, so in this case, when we talk about the aqueous solution at this point in time, the examples is if your acid or if your base reacts with water, the products are going to be formed. But in this case, when the products are being formed, we can see that we're going to have a presence of concentration of H3O plus ions in a solution. What does that mean? That means the solution will be acidic because it's acid and water, therefore the solution will be acidic. And then the type of acid that we see over here, it is called the monoprotic acid. Why do we call it a monoprotic acid? Because it is eligible to donate only one proton. Recall that according to Laurie Braustedt theory, they say that acid, it is a proton donor. So in this case, our HCl, it is an acid. It will donate its proton. And then by the way, in this case, water will be behaving as a base. When acid and water reacts, then water will accept that proton, and then we're going to have these products that we see over here. We can see now water has turned to be H3O plus ions because it has accepted the proton. And we can also see that HCl, it has turned to be Cl minus ion because it has donated the proton. This one, it has accepted the proton. And then by the way, because we have donated only one proton, therefore HCl, it is called monoprotic acid. Another example over here is we can see ammonia reacting with water to form the ammonium ions. So like I said, ammonia, it is a base, it will have to accept. Now in this case, water was reacting as a base, but now water reacts as an acid. In this case, water will be the one that's going to donate a proton. When water donates a proton to ammonia, we can see that water will turn into OH minus ions. And then ammonia will accept that proton, it will turn into NH4 plus ion, which is called the ammonium ions. So during this chemical reaction, we can see we have an indication of OH minus ions concentration. So that means the solution, it will be basic. Okay. All right. Now here's another type of reaction. We can see that we have um, sulfuric acid, which is H2SO4, reacting with water, two molecules of water. So that means this is an acid. It will donate acid two times because we have H2, unlike there where we have H1. We have H2, the subscript over there. So that means sulfuric acid will donate hydrogen protons two times. So this type of acid, it is called the diprotic acid because it donates two times. If it has to donate three times, it will be called polyprotic acid. So in this bulletin, the idea was to look at the reactions of acids underwater. Okay, and then these are the products that are being formed. This is dissociation and ionization of acid, dissociation of our base. Awesome. Now, bulletin number 3, what we need to look at is we should be able to see what is a conjugate acid-base pairs for a given compound. Now, when it comes to the conjugate base, these things, I will explain this much more better when we go through the course, because remember, this is just the guideline. So this one, I need to do it looking at the reactions, okay? So we will look at it at the later stage. And then this bulletin over here, it talks about the ampholyte. Like I said, water, it acts as an ampholyte, but not only water acts as an ampholyte. Recall that when you talk about the ampholyte, we are talking about the substance that can react, that can act as either acid or a base. That's an ampholyte, okay? Like I said, water is a good example of an ampholyte substance, okay? So, in this case, we can look at it over here. I told you that here water will behave as a base, right? It will accept the proton. It's going to be H3O plus ion. And then here it will behave as an acid where it will donate a proton and then it will turn into OH minus ions. So that's an ampholyte, a substance that behaves like that. We say it is an ampholyte. Now recall that I said acid can react with water, base can react with water, just like how we saw over here. And then I also indicated that acid can react with base, right? So this is what now we are actually going to look at in terms of chemical reaction. And this type of reaction, it is called the neutralization reaction, okay, of common laboratory acids and bases. Now, when acid and base react, it's important on what type of acid is reacting with what type of a base. Because the products that are going to be formed during this chemical reaction depends on what is reacting, which does make sense, right? So here we take acid, we take base, but here we took acid and water, or we took base and water, and then we saw how everything behaves. But now here we're going to take acid and base. We can see that hydrochloric acid can react with sodium hydroxide. In this case, we have two strong acids, strong acid and a strong base. Like I said, it's important what type of acid is reacting with and what type of base is reacting. Are we having a strong acid and a strong base? Are we having a strong acid and a weak base? Are we having a weak acid and a strong base? Are we having a weak acid and a weak base? It depends on what, and again, the type of acid that is reacting. Like I said, we have numerous types of examples of these substances, right? So now, here we have hydrochloric acid reacting with sodium hydroxide. We can see that it's an acid reacting with your base. I'm writing with this thing. You have your acid reacting with your base, right? Right. Even potassium hydroxide, it is the base, strong base. Both of them are strong. And then now, what I want you to understand, or what I want you to pay attention onto is when acid reacts with base, we're gonna form this product over here. Sometimes we form water, sometimes we form carbon dioxide. Most of the times you will form, like I said, it depends on a type of an acid and a base that are reacting together. So we form water. The reason why we have water is because of we are neutralizing. It's neutralization reaction. Okay, so when an acid reacts with base, it forms water. Sometimes we form carbon dioxide. But the other thing that I want you to pay attention on to is this product over here. This product over here, it is called the salt. It's an ionic compound. We also form a salt during this chemical reaction. We can see even here HCl reacting with this base, it forms a salt. HNO3 reacting with NaOH, it forms a salt. This and this, it forms a salt. This and this, it forms a salt. This and this, it forms a salt. So the salt that is going to be formed, it depends on the reactants that are being used, right? And then water will be the part of a product most of the times, all the times. Sometimes we have carbon dioxide because it's a neutralization reaction. Now, again, what's important during these chemical reactions is that what strengths of bases and acids are interacting. Are we having a strong and a weak and what and what? Again, I have already explained that. That's also very important because a salt that is going to be formed over here, it will undergo a reaction called hydrolysis. So when you have a look over here, we have what we call the hydrolysis. So that means these hydrolysis, we define it as a reaction of salt with water. Now, here's the thing. When acid react with base, my question is, look, when acid react with water, the solution will be acidic. When a base react with water, the solution will be basic. Now, when the base react with acid, will the solution be acidic? Will solution be basic? Or will solution be neutral? Meaning neutral, the acid and base, they balance each other. Therefore, the pH of solution becomes 7. Do you understand? So what's going to help us to determine the solution of water? It is the salt that is going to be formed during this chemical reaction. Now, this salt, we're going to take them and then they will undergo what we call the hydrolysis. These salts will react with water, and it's important, like I said, the salt that is formed over here is important. It was formed from what type of a base? A strong base or a weak base, a strong acid or a weak acid. The salt that is formed over here, it will undergo hydrolysis to determine the pH of the solution. So, like I said for the last time, hydrolysis, it is a reaction of salt and water. Okay, so then in this bulletin, we'll be looking at on how to determine the approximate pH. So it's either pH 7 or less than 7 or above 7. Okay, so like how it is shown over here. The highlight or the key highlight that I want you to take is during the hydrolysis, if you take your weak acid and a strong base, the pH will be less than 7, meaning, sorry, greater than 7, meaning we're going to have an alkaline solution, which doesn't make sense. You have a strong base and a weak acid. Definitely, you expect solution to be more basic, to be basic than, and therefore, example of such salt is sodium ethanoate. You should understand where does this sodium ethanoate coming from. Here it is. This is ethanol. Ethanol reacting with sodium hydroxide, it forms sodium ethanoate. So sodium ethanoate, it is this salt, right? Um, This salt will result into a solution that is basic because the pH will be more than 7. So how was this sodium ethanoate formed? Sodium ethanoate, it was formed by a ethanoic acid and sodium hydroxide. And you can see that this ethanoic acid, This ethan is carboxylic acid. Yeah. This ethanoic acid, it is a weak acid, and sodium hydroxide, it is a strong base. So, like I said, a weak acid and a strong base, they form an alkaline solution. Alkaline solution meaning it is a basic solution. So, examples of those salts are sodium hydroxide, ethanoate, and then we also have sodium oxalate from this is sodium oxalate from oxalic acid, right? And then another type of a salt, where is it? It's sodium oxalate and sodium carbonate. Now, where is sodium carbonate coming from? Let me see. Do we have it here? I don't see it. No, I don't see the sodium carbonate. Now, if we have a strong acid and a weak base, solution obvious will be acidic. Strong will dominate. So strong acid and a weak base, then the solution will be basic because we have a strong acid over a weak base. Now the pH definitely will be less than 7. And then examples of salt, it is ammonium chloride. So this is ammonium chloride. This is ammonium chloride. We can see that HCl, which is a strong acid, it reacts with sodium carbonate, which is a weak base. Now, strong acid, weak base, sodium chloride. And then this sodium chloride, it is an example of a salt that will result into a solution that is acidic, whereby the pH will be less than 7. And then again, strong acid, strong base, strong, then does not undergo hydrolysis at all. Very important. Do not undergo hydrolysis. And the solution of the salt will be neutral. So meaning the solution of salt will be neutral. So meaning if you take your HCl and NaOH, we form this. Yes, if you even this salt, depending where is the salt coming from, or you take your KOH and HCl, we definitely going to form KCl. KCl, this salt will result into a solution that is neutral. Okay, that is neutral, whereby the pH will be equals to 7. Then again, like I said, we'll go through the content and see how these things actually work. Now, we will also focus on the acid-base titrations. So, what's the purpose of titrating? What is titration and what is the purpose of titrating? Now, titration, it is when you add base into acid or acid into base in terms of acid and base titration, okay? So when you take your acid and then you add it into base, that's titration, or you take your base, you add it onto acid, that is a titration. Now, what is the purpose of titrating? Is to determine the concentration of the unknown. We have two species, right? We have acid and we also have base. Let's say acid, we have a known concentration, but the base, we don't know its concentration, meaning its concentration, we say it is unknown. So in order for us to determine the concentration of base, we're going to have to perform what we call titration. By the way, since well the base it has a known concentration, what do we call this substance? We call it a standard solution. A standard solution can be prepared when you perform your calculations or whatever, or a standard solution can be given. You need to prepare your standard solution. You will see when we do more complex calculations that how to perform your standard um, concentration. Okay, you perform it because you're gonna know its concentration by performing your stoichiometric calculations. And then in order for you to calculate or to know the concentration of base, you're gonna have to perform what you call titration. Still, we're gonna do your um what's this your stoichiometric calculations though, but after titration you will see, because we're going to have known parameters, we're going to have to determine the volume that we're going to use when we titrate. You will see that. So again, there's so many different times under titrations. We are looking at the equivalence point, we are looking at the end point. What is it? There it is. We are looking at the end point and such things. Standard solutions, you need to know those terms. Okay, so when we reach the end point, this is the point where the indicator changes. Oh, by the way, we have three types of indicators that we're going to talk about. We have methyl orange, we have phenolphthalein, we have bromothymol blue. These are all um what is this? These are all indicators that we're going to make use of when we perform acid-based titrations. And then again, when we talk about the endpoint, that's where the color change will start to show. And then when you talk about the equivalence point during titration, that's where the number of moles of acid and base are now equal. But like I said, titration, obvious, me explaining it through the guideline, it will be a little bit tricky and challenging, but we will do it as it is under the concept, okay? Right. Then this is where you're gonna perform the stoichiometric calculations. We will see all of this. Okay. All right. And then again, we should be able to know how to list the apparatus needed or identify the apparatus from a diagram. So how I'm explaining this guideline, it will be much more better if you have already dealt with a base. Maybe you still want to understand, but if it's your first time hearing more about this in base, I will go through it step by step. Okay. So me explaining this is for someone who has already done this part. Okay. By the way, it's because it's a guideline. And then yeah, we'll talk all of these things, apparatus such as burette and all of those things, the diagrams, the procedure, how to perform a standard oxalic acid solution, like I said, a known concentration. We need to know how to describe the procedure to conduct the titration. You will see which one are we going to put inside of the burette, LMAR flask. We swell while we titrate. There's so many things involved during titrations. We'll discuss those procedures. And then again, we will describe the safety precautions that you need to take, whether you add acid when you dilute, you add acid in water or water. Those are the safety precautions that we're going to look at. Okay. Then again, describe the measures that needed to be in place to ensure reliable results, and interpret given results to determine the unknown concentration. The given results to determine the unknown concentration, which is we're gonna do that through the titration, definitely. Sometimes we will be given the given experiment. We just need to interpret sometimes. Obvious, you can't do experiment unless if you guys do it in class. And then the pH and the pH scale, we're gonna have to explain the pH where we use the equations. Now, this is more of calculating the formula that we use to calculate the pH or the POH. We use hydrogen ions, and then when we want to calculate the POH, we use um, hydro hydroxide ions. You will see that, okay, when we perform the calculation. So this, then we're gonna talk about the ionization constant of water or ionic product of water, which is denoted by this equation. You can see that is 1 times 10 to the power 14, which is neutral at standard temperature, which is 298 Kelvin. And we're going to have to also focus on the auto-ionization of water, which is the reaction of water with itself when water reacts with itself. Recall that water and water, it can be basic or it can be acidic. That is auto-ionization. Auto means automatic, right? Automatically reacting by itself. It will form OH minus ions, it will form H3 plus ions, and then we're going to have to interpret the Ka. This is the ionization constant for acid, ionization constant for base. We're going to determine the relative strength of given acid using that. Here, definitely of base using that. Then compare strong and weak acids by looking at their pH, whether monoprotic or diprotic. We're going to look at the conductivity, which solution can conduct electricity, so forth. Then we're gonna look at the reaction rate, which is now combination of reaction rate and acids and bases. Okay, and this kinda also during the calculations it involves chemical equilibrium, but yeah, we will see how we go there. Then for this guideline, I will end it here, and this is just a let me do this. This is just a mind map on how this actually works, right? It's everything that I have already discussed. And yeah, this mind map, it actually takes us on where to start and how to move. And that's it with this guideline.